Students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as Atoms, Molecule and Nuclei. Let's see this. What is the origin of spectral lines? Now, let's try to understand what are spectral lines. Now, the origin of spectral lines, specifically in hydrogen atom, can be explained by using Bohr's atomic theory. Right? Now, when hydrogen atom, I'm going to consider for hydrogen atom first. Let's see the origin of spectral lines in hydrogen atom can be explained by using Bohr's atomic theory. Right? Now, according to Bohr's atomic theory, when a hydrogen atom is in its normal state, the electrons revolve in the innermost orbit, right? That is the orbit for which the principal quantum number is 1. When hydrogen atom is in its normal state, the electrons revolve in its innermost orbit. Right? Now, this energy state is the lowest energy state of the electron and it is called as the ground state. This energy state is the lowest energy state and is called ground state of the electron. So basically, so far what we have said is that the electron is rotating in the innermost orbit, that is the first orbit where the principal quantum number is 1. No extra energy given to it. Now, let's assume that the hydrogen gas is subjected to some kind of radiation or is heated directly or is given some electric field. In that case, hydrogen gas would receive some energy. Due to this energy, if I heat hydrogen gas, it will receive some energy. I can say that if hydrogen gas is subjected to some kind of radiation, then hydrogen atoms receive energy. Right? Now, this energy which is received by the hydrogen atom, how does it use it? There are two things that will happen to this. There are two cases that may arise. First, the energy absorbed is equal to or greater than 13.6 electron volts. Suppose if the energy that is given to hydrogen atom is greater than 13.6 electron volts, which is called as the ionization potential. We had seen in the previous lecture that the energy possessed by an electron in any orbit is 13.6 upon n square, right? So if the energy that is absorbed by hydrogen atom, electron in the hydrogen atom, is greater than 13.6 electron volts, then the electron will have sufficient energy to jump the orbit and go into the next orbit. For the electron to jump from one orbit and go into a higher orbit, it should be given 13.6 minimum. 13.6 electron volts of energy, right? So I can say that if the energy absorbed is equal to or greater than 13.6 electron volts, the electron leaves the atom and escapes out. Electron leaves the atom and escapes out. Why escapes out? Because in the case of hydrogen atom there is only one orbit, right? Now this is if it is greater than or equal to 13.6 electron volts. If the energy absorbed is less than 13.6 electron volts, if the energy absorbed is less than 13.6 electron volts, right, then the electron will jump from the innermost orbital or innermost orbit to the outer orbit of higher energy level, and the electron begins to revolve in that orbit, and in that case the atom is now said to be in excited state. Remember, when you were doing hybridization, you had learned that during the process of hybridization you first send the atom into excited state and then hybridization takes place, right? So if the energy absorbed is less than 13.6 electron volts, the electron jumps from the innermost orbit to the outer orbit of higher energy level, and begins to revolve in it. Right? Now as a result, the atom is now said to be in excited state. The atom is now said to be in excited state. Right? Now this atom which is in excited state, since it is in excited state, therefore it is going to be unstable. An atom which has absorbed more energy than it is required is going to be unstable. First thing it is going to try to do is it is going to try to give out that surplus energy that is stored in it, right? So it is going to try to give out that surplus energy. How will it give out the surplus energy? By pushing the electron back to its ground state, right? Do you get this thing clear? So I can say that this atom in excited state is unstable, and therefore it returns back almost immediately to its stable state, right? In doing so, the electron returns to its ground state in one or more steps. If energy is given out, that energy was stored in that electron which had jumped to a higher energy level. If energy has to be given out, that energy which was stored in the electron at high energy level is going to be given out in energy, and the electron is going to be pushed back to the ground state. So I can say that in doing so, the electron returns the electron returns to its ground state. The electron returns to its ground state and starts revolving around the nucleus. And starts revolving around the nucleus. Right? Now, according to Bohr's theory, or according to Bohr's third postulate, when the electron jumps from a higher energy level to a lower energy level, it gives out some energy, right? Which corresponds to the difference. Between the energy levels of the corresponding orbit. Now, I can say by Bohr's third postulate, if I apply Bohr's third postulate, during such transition, that is, when the electron is jumping from higher energy level to lower energy level, during such transition, the electron radiates energy. The electron radiates energy equal to the difference between the energy level between the energy levels of the corresponding orbit. Right? This energy is radiated in the form, if it is going to give out energy, Bohr's third postulate says that this energy is going to be given out in the form of photon energy. This energy is given out in the form of photon energy, right? Now let's assume that En is the energy in the nth orbit. Right? Let us assume that Ep is the energy in the pth orbit. Right? Now let's assume En is the energy in the nth orbit, which is the outermost orbit where the excited electron had gone, and P is the inner orbit. Right? That means I can therefore say that En is going to be greater than Ep. Why? Because simple, N is greater than P. The energy in the higher orbit is going to be obviously more than the energy in the lower orbit. Now, we have already found out how much is the energy in a particular orbit, but I can say that energy in the nth orbit is minus me4 upon 8 epsilon 0 square n square h square. We have derived this. Right? Similarly, energy in the pth orbit will be minus me4 upon 8 epsilon 0 square p square h square, because here the orbit is p. Now, according to Bohr's third postulate, when the electron jumps from an outer orbit of higher quantum number to a lower orbit of smaller quantum number, it radiates energy which is in the form of photon of frequency v. Remember Bohr's third postulate, En minus Ev is equal to hv. So I can say by Bohr's third postulate, by Bohr's third postulate, when an electron jumps from higher energy level to lower energy level, it gives out energy, radiates energy in the form of photon of frequency v. Therefore, I can say that HV is equal to En minus EP. HV is going to be, I'm straight away just writing Bohr's third postulate, right? Now I know the value of En and EP, so I can say HV is equal to minus Me4 upon 8 epsilon 0 square n square h square minus Me4 upon 8 epsilon 0 square p square h square, right? Here I could take HV is equal to, I can take Me4 upon 8 epsilon 0 square h square common. So in that case this will become minus 1 upon n square, minus into minus 1 plus 1 upon p square. So this is going to be equal to, if I take h down in the denominator, I'll get V is equal to Me4 upon 8 epsilon 0 square h cube 1 upon p cube, 1 upon p square minus 1 upon n square. That h square became h cube. So this will be the frequency with which photon is going to be given out. This is going to be the frequency with which light energy is going to be given out, right? Now in that case I can say that, but if lambda is the wavelength, then I can say that frequency is c upon lambda, right? In that case I can say that frequency is c upon lambda. So I can therefore say that I want to find out 1 upon lambda. So I can say that 1 upon lambda is nothing but V upon C. V I already know, substitute the value of V. So I'll get 1 upon lambda is Me4 upon 8 epsilon 0 square C h cube 1 upon p square minus 1 upon n square, right? Now this is known as Bohr's formula, right? This is going to be my wave number, right? This is known as Bohr's formula, right? Once I have Bohr's formula, then I can say that here, let us assume that Me4, mass of the electron, charge on the electron, permittivity of space, velocity of light and Planck's constant, all are constant. Let us assume that this is equal to R. So in that case I'll get 1 upon lambda as R times 1 upon p square minus 1 upon n square, right? Where R is called as Rydberg's constant. Fine. Now, if I substitute all the values, it has been experimentally found out, or if I mathematically found out that the value of R is 1.097 into 10 raised to 7 per meter. Right? That's going to be my value of R. Fine, do we get this thing here? So do you understand the origin of spectral lines? Why do you have spectral lines? Because when an atom absorbs some heat energy, the electron jumps. Now either the electron can directly jump into the next orbit, or it can remain in an orbit that is between the two orbits. Right? If the electron has absorbed 13.6 electron volts, then it will directly jump into the next orbit, no problem at all. But if the electron has absorbed energy less than 13.6 electron volts, then it will remain in the transition state between the two orbits. Right? Since it is in that transition state, it has absorbed energy more than what it should have in its own orbit, but less than what it should have in the subsequent orbit. That means it is going to be somewhere in between. Hence it will be in unstable state. As it is in unstable state, it will quickly try to bring itself into stable state. In doing so, it is going to jump from that higher energy level to lower energy level. As it jumps from higher energy level to lower energy level, it will give out a photon energy of frequency V, and that is what gives rise to spectral lines. Right? Do you understand this? Okay. Now that we know the origin of spectral lines, so why do we have spectral lines? Spectral lines is when there is a transition of electrons from outer quantum number to inner quantum number, a spectral line of wavelength lambda is given out. Fine, do we get this thing here? So the equation suggests that a series of spectral line would be given out. Now again, what kind of spectral line would be given out will depend upon from which energy level is the electron jumping. Is it jumping from the second orbit to the first orbit, third orbit to the first orbit, fourth orbit to the first orbit? Obviously the orbit that it is going to jump from, my value of n will change. As my value of n changes, the value of lambda will change. That means if the electron jumps from a different orbit, I will get a light of different wavelength. Right? The wavelength of light that I will get will depend upon from where is the electron jumping. Right? So I can say that from the equation it is very clear that the spectral lines obtained by the transition of electrons from different orbits to a fixed inner orbit would be different. Right? Now let's see what are the different types of spectral lines that you can get. Second, types of spectral lines. First is called as Balmer series. Right? What is Balmer series? It is a series of spectral lines arising from the transition of electron from different outer orbits to an inner orbit of quantum number p is equal to 2. If an electron jumps from any outer orbit to an inner orbit where the quantum number, principal quantum number is 2, then what you get is called as Balmer series. Right? So it is a series of spectral lines arising from the transition of electrons from different outer orbits to a quantum number p is equal to 2. Right? So in that case, what will be my wavelength? Then my formula will be 1 upon lambda is R 1 upon p is equal to 2. So this will be 2 square minus 1 upon n square. So what you have to remember is that for Balmer series, the value of p is going to be 2. the electron is going to jump from different outer orbits to a fixed inner orbit where principal quantum number is p is equal to 2. Now, let's talk a little more about Balmer series. Balmer series is a series of spectral lines which lie in the visible region, which have wavelength somewhere between 4000 to 8000 Armstrong unit. Fine, do we get this in here? Okay, so that's Balmer series. Next, let's see what else can I have. I can have Lyman series. What is Lyman series? It is a series of spectral lines which arise from the transition of electron from different outer orbital to a quantum number where p is equal to 1. So if they jump from the outermost orbit to the innermost orbit, from any outer orbit to the innermost orbit, then what you get is called as Lyman series. Fine, do you get this thing here?
So then P will become 1, right?
Excuse me?
Then P will be the
Yes,
1.
P will be 1. It is a series of spectral lines arising from the transition of electrons from different outer orbits to a quantum number p is equal to 1. Fine, do you get this in here? So in this case, for Lyman series, my equation will be, for Lyman series, my equation will be 1 upon lambda is equal to r 1 upon 1 square minus 1 upon n square. Right, do we get this in clear? So do we understand Lyman series? Let's talk a little more about Lyman series. Lyman series are it is a light where the wavelength is in the ultraviolet region. So it is not in the visible spectrum. It is in the UV spectrum, ultraviolet region spectrum. Okay. Next, let's see next Paschen series. Right, when it jumps to principal quantum number 3, when you have transition of electrons from any outer orbit to an orbit where the principal quantum number is 3, that means to the third orbit, then that is called as Paschen series. Fine, do we get this thing clear? So I can say that a series of spectral lines which arise from the transition of electrons from different outer orbits to a quantum number p is equal to 3 is called as Paschen series, right? So the equation for Paschen series will be 1 upon lambda is r times 1 upon 3 square minus 1 upon n square. That is going to be my Paschen series, right? Now, Paschen series is near the infrared region. The spectral lines that are given out are near the infrared region in the case of Paschen series. Okay. Next, you have bracket series. What is bracket series? Where you would have transition of electron from any outermost orbit to an orbit where p is equal to 4. So very similar to what we've been doing. So it is a series of spectral line which arise from the transition of electrons from different outer orbit to a quantum number p is equal to 4, right? Hence I can say that 1 upon lambda is r times 1 upon 4 square minus 1 upon n square, right? Bracket series is obtained in the far infrared region, so they are extremely embedded in the infrared region, right? Next, T-fund series. Right, what is P-fund series? It is a series of spectral lines which arise from the transition of electrons from different outermost orbit to a quantum number p is equal to 5. Right? So, very simple again, a series of spectral lines which arise from the transition of electrons from different outer orbits to a quantum number p is equal to 5. So I'll get 1 upon lambda is r times 1 upon 5 square minus 1 upon n square. Fine, do we get this thing clear? Now, the P-fund series is also deeply embedded in the infrared region, right? How do I show a diagram for these spectral lines, right? Spectral lines. Let's try to see the diagram for spectral lines. You would have let's assume that this is my ground state. Ground state where n is equal to 1, right? This has energy which is equal to minus 13.6 electron volts, right? Now, if you have light, if you have electron jumping from any outer orbit to this orbit, then that is called as Lyman series. That means if you have electron jumping from here to here or here to here, from any outer orbit it is jumping to the innermost orbit, then that is called as Lyman series. Those are the series of spectral lines where the electron jumps from any outer orbit and to this, the innermost orbit. This is my Lyman series. So this is those series of spectral lines. Right? Now let's assume that this is n is equal to 2. Now this is Lyman series is in the UV region. Now let's assume that here n is equal to 2. So in that case, n is equal to 2 has energy minus 3.4 electron volts. Okay. Now, in that case, if you had electron jumping from the outer orbit to E is equal to 2, then what you would get would be called as Balmer series. What you would get is Balmer series, which would be like this. From a high energy level, you are jumping to this. This is my Balmer series. where the electron jumps from an outer orbit to an orbit where the quantum number is E is equal to n is equal to 2. Okay, now this is in the visible spectrum. Like I said, Lyman series is in the UV spectrum, Balmer series is in the visible spectrum. And then you can have similarly n is equal to 3. Suppose if I take n as 3, if n is equal to 3, then E is minus 1.57 electron volts. So if you had transition of electron from any orbital, from any orbit to quantum number E is equal to 3, then what I would get is called as Paschen series. So here I would have Paschen series that would be like this. Right? This is going to be my Paschen series. Right? So that's how you show your spectral lines. Similarly, you could also have the bracket series and P-fund series for electron jumping into that particular orbital. For example, if I consider n is equal to 4, then the energy in this orbit is minus 0.85 electron volts. So if you had transition of electrons from outer orbits to n is equal to 4, in that case what you would get would be called as your bracket series. This is going to be my bracket series, right? This is bracket series, right? Once you have the bracket series, finally you could also get your P-fund series. P-fund series is when n is equal to 5. The energy in that orbital is going to be almost negligible. So you would have very small energy there, and you would have transition of electrons from an outer orbit to E is equal to 5. Fine, do you get this idea? So do you understand the origin and how spectral lines are formed? Now, once we understand spectral lines, we also understand that when there is a transition of electrons, when there is a transition of electrons from the outer orbit to any inner orbit, energy is given out, and that energy is given out in the form of photon. That means that energy is going to be given out in the form of light energy. That light energy is going to have some specific frequency. Now let's understand this concept very clearly, because yes, I'll write that energy. Just give me 2 minutes, right? Let's understand this concept very clearly, because I need this concept for something which is called as laser, right? I just calculate that energy and give you 2 minutes, right? Next we have second, third, laser, right? Let's start with laser. Now first of all, question: why do I need laser light? I already have ordinary light. I have this simple light. Why do I need laser light? Now there are certain problems with our ordinary light. The problems that we have with ordinary light, with monochromatic light, is that first of all, I cannot use white light because it will have more than one wavelength. You will say, sir, I can solve that problem by using a monochromatic light. Let us assume that if I use monochromatic light, a monochromatic light, guys, has angular divergence. Instead of moving this way, it will move this way. It has angular divergence. The monochromatic light has angular divergence, as a result of which the ray of light has poor coherency, right? Due to its poor coherency, it cannot travel large distances because it is going to be dispersed over a very large area, right? It also suffers from the phenomenon of diffraction. Remember, we had done what is diffraction, right? That is when it passes through sharp edges, there is going to be bending of light, right? As the if I increase the intensity, any object, a small object coming in its path, would result in its diffraction. So as a result of this, an ordinary light is not capable of moving to large distances. If I want to project a light over a large distance, I cannot use ordinary light. Multiple reasons. A, I cannot use white light because there is going to be multiple wavelengths. If I use monochromatic light, it has very high angular divergence, it suffers from diffraction. It has very poor coherency, right? These are my limits. It will not stick together. It will not move as a beam. For it to move as a beam, it should be coherent. Remember we had done this, that in order to have a clear interference pattern form, coherency is necessary. They should be derived from the same source. We had done this in Young's experiment, where we had done a double split. Coherency, that means if the light is traveling in the form of a beam, the crests and the troughs, or the compressions and rarefactions of the beam should match with each other, right? Okay. So now do we understand what are the limitations of ordinary light, and that is the reason why ordinary light cannot be used. Hence we use a different kind of light which is called as laser. What do you mean by laser? Laser stands for laser. Laser stands for light amplification. Light amplification by stimulated emission of radiation. Emission of radiation. Right? So it is nothing but it is a method of amplifying light. What is laser? Laser is a method of amplifying light. Now how do I amplify light? In order to amplify light, before I can actually understand how I amplify light, I need to understand a few basic concepts. Right? Let's see what are the terminology that I will need before I start amplification of light. Induced absorption. What do I understand by induced absorption? Now let us consider that you have a lower state energy level E1 and a higher state energy level E2. Now as per Boltzmann, that's another scientist, as per Boltzmann's distribution, the ratio of number of atoms present in the higher energy level to the ratio of number of atoms present in the lower energy level can be given by a specific formula. You would have certain number of electrons that would be present in the lower energy level. You would have certain number of electrons that would be present in the higher energy level, right? What is that ratio? Because if I want to stimulate light, I need, see, if I want light, light can be produced only when the electron jumps from a higher energy level to lower energy level. For that, I should first of all know how many electrons are there in the higher energy level. Fine, do you get this thing clear? So, I can say that, consider, let's first find out how many electrons are there in the lower energy level, how many are there in the higher energy level. Okay, consider lower state energy level, E1 and higher state energy level E2. Right? In which case, according to Boltzmann's distribution, according to Boltzmann's distribution, the ratio of number of atoms, the ratio of number of atoms the ratio of number of atoms present in higher energy level, present in higher energy level to the number of atoms present in lower energy level the number of atoms present in higher energy level to the number of atoms present in lower energy level at temperature T. Number of atoms is N1 in lower energy level and N2 in higher energy level. This ratio N2 upon N1, that means the number of atoms present in higher energy level to the number of atoms present in lower energy level, is given by the formula E raised to minus E2 divided by KT upon E raised to minus E1 divided by KT. Right? That is the formula. That means I can therefore say that N2 is equal to N1 by using law of indices. This is going to be E raised to minus E2 upon KT, minus into minus plus E1 upon KT, right? So in that case, this is going to be nothing but N2 is going to be equal to N1 E raised to KT can be taken as common. So in that case, this is minus E2 minus E1 upon KT. I'm taking minus sign common outside, right? Now we already know that E2 is greater than E1. We already know that E2 is greater than E1. If E2 is greater than E1, therefore it is obvious that N2 has to be less than N1. If E2 is greater than E1, then N2 is going to be less than N1. That means the number of electrons that are going to be present in energy state E1 is going to be more than the number of electrons present in higher energy level. For light to be formed, I need electrons jumping from higher energy level to lower energy level. If there are no electrons in the higher energy level, they will not jump down, light will not be formed. Right? Do you understand what is the basic problem in having laser? To have laser, I should have more number of electrons at higher energy level, which I can kick and push them down in the lower energy level. If there are no electrons only there, what will I push down? Right? Do you understand this? So I can say that that is the number of electrons present in state E1 is greater than the number of electrons present in state E2. The number of electrons present in state E1 is greater than the number of electrons present in E2. Now, for higher temperature, as the temperature increases, N2 will increase. That means as the temperature increases, the number of atoms in the excited state E2 will increase, right? But as temperature increases, the number of electrons in E2 will increase, right? In that case, as E2 again becomes greater than E1, as the temperature increases, also as temperature increases, E2 will become greater than E1, right? If E2 becomes greater than E1, again N2 will become less than N1. So if you were to give me an argument that, sir, I can have more electrons in the higher energy level just by increasing the temperature, because if I increase the temperature, I would be exciting those electrons in the high energy level. Yes, I agree with you. But as E2 becomes greater than E1, then there would be the number of electrons that you would push to high energy level will be far less than the number of electrons that would be there in the lower energy level. So the idea of increasing the temperature and having more electrons at high energy level does not work, because if E2 becomes greater than E1, then N2 will become more smaller by using the Boltzmann ratio, right? Do we understand this? That means I can also say that if V is the frequency of radiation, then by Bohr's third postulate, says that frequency is going to be E2 minus E1 upon H, right? That is, you would have the frequency of radiation is on an incident surface can be raised if I have more number of electrons in the higher energy level, right? Or if there is a large difference between the higher energy level and the lower energy level, right? So I can say that if the frequency of the incident energy is raised, then I can have more electrons in the higher energy level. Instead of raising the temperature, if I change the frequency, then I can have more number of electrons at higher energy level, and this process is called as induced absorption of light. What is induced absorption of light? If the radiation of frequency is incident on a surface, if the radiation of light is incident on a surface, more atoms will be raised to higher energy level, E2, by absorbing the photon energy. That means if I want to push electrons to a higher energy level, instead of heating it, what I do is that surface, I'm going to have light incident on that surface. If light becomes incident on the surface, that means photon energy will become incident on the surface. That photon energy is going to push the electrons, that will push more electrons at high energy level at the same temperature. Right? This process of pushing more number of electrons at higher energy level by making a light beam incident on the surface is called as induced absorption. Do you understand what is induced absorption? Right? And why do I need induced absorption? So that I can have more electrons at higher energy level. Do you understand this? So I can say that if a radiation of frequency V is incident on a surface, more atoms will be raised to higher energy state. More atoms will be raised to higher energy state. More atoms will be raised to high energy state E2 by absorbing the photon of energy, HV. Right? This process is called as induced absorption of light. This process is called as induced absorption of light. Right, so do you understand what is induced absorption? Next, let us see what is next concept we have is spontaneous emission. What do we understand by spontaneous emission? Right? Now, we know that the lowest energy level is called as the ground state, right? And we have higher energy level which is referred to as excited state. So the electron can be in the ground state or it can be in the excited state. Now, the excited energy level is usually unstable, right? And the electron in these excited state immediately returns back to the ground state, either in one jump or more than one jump, emitting a photon of definite frequency, carrying a definite wavelength. Now, the frequency, that is the frequency of light that will be emitted, will depend upon the difference between the two energy level by Bohr's third postulate, right? Such an emission that results in the transition of electrons from higher energy level to lower energy level without any external agency is called as spontaneous emission. Simple. If an electron is there in excited state, what will happen? Excited state is an unstable state. If an electron is there in excited state, the first thing that it will do is it will try to come back to ground state. In doing so, it is going to give out energy in the form of photon, right? What will be the frequency of that energy? The frequency of that light photon will depend upon the difference between the two energy level, right? This process of an electron jumping from excited level to ground level without any external agent is called as spontaneous emission. So if an electron is there in excited state, it will automatically jump to the ground state. This process is called as spontaneous emission, and in doing so it will give out a photon of frequency V, where V will depend upon E2 minus E1 upon H. Right? Do you get this in here? It will depend upon the difference between the two energy level. H as it is Planck's constant. Right? So do you understand what is spontaneous emission? I can say that the lowest energy level is called as the ground state energy level. The lowest energy level is called as the ground state energy level. The lowest energy level is called as the ground state energy level, and the higher energy levels energy levels are referred to as excited energy level. Right? Now, the excited energy levels are usually unstable. Excited energy levels are usually unstable, and the electrons in these excited energy level excited energy levels immediately return to the ground state. Right? These electrons immediately return to the ground state. emitting a photon of definite frequency, emitting a photon of definite frequency, emitting a photon of definite frequency and carrying an energy equal to the difference, and carrying an energy equal to the difference, carrying an energy equal to the difference between the corresponding energy levels. The corresponding energy levels. Fine, do you get this thing here? Such an emission resulting due to the transition, such an emission resulting due to the transition, from higher energy level to lower energy level without any help of external agency, is called spontaneous emission. Right? So that is spontaneous emission. Next, let's understand what is stimulated emission. Let's try to understand what is stimulated emission. Now, let us consider that an atom with an electron in high energy level. So let us assume that this is an atom, this is a nucleus, this is the electron revolving at high energy level. This is my electron, it is at high energy level. Here is my nucleus, right? So let us consider, guys, an atom with its electron in high energy level. Now, let us suppose a photon of correct energy. What do you mean by correct energy? Correct energy means the difference between the electron's energy level and lower energy level. The electron is here at this energy level. It should have been here. This is the ground state, this is the excited state. The electron is in excited state. Now when it jumps from excited state to ground state, it is going to give out some energy which is equal to the difference between the energy. Due to that difference of that energy, there is going to be some photon that will be given out which will have some frequency which is E2 minus E1 upon h. Right? It will have some frequency. Now I am going to target this electron with an external photon which will have frequency equal to that frequency. I am going to target this electron with a photon whose frequency will be equal to E2 minus E1 upon h. Externally I am giving this. Right? So suppose a photon of correct energy from some external source collides with the atom. So let's bring a photon. So this is the photon and it collides. Right? Now it collides, thereby emitting a photon. Right? Now when it collides, what will happen? When it collides, it's going to emit a photon. Right? When it collides, that electron is going to jump from higher energy level to lower energy level. As it is, it was going to jump from higher energy level to lower energy level. So in that case, you would have electron. This is your spontaneous absorption. I already explained to you what is spontaneous absorption. By putting a light energy incident on a surface, pushing the electron from lower energy level to high energy level. So I have pushed the electron there. Now once I have done spontaneous absorption, the electron due to this photon has jumped from the lower energy level to higher energy level. Now let's get back to the atom. Nucleus, the electron is here. Once it reaches in the high energy level, it is going to be unstable, so it would want to jump down again. There is going to be a spontaneous emission. There is going to be a spontaneous emission that will push the electron down. So the electron is not going to be there anymore. It will come back to its ground state. This is going to be my spontaneous emission. During this process, it will give out an energy of some photon, give out a photon energy of some frequency, right? Now I make light incident on the surface. If light is incident on the surface, the electron will jump from the ground state to the excited state. Once it goes into the excited state, it will jump from the excited state back to the ground state. Now during this process, when it is jumping down, that means when the electron is coming down from the excited state to the ground state, this electron which is going down, if it collides with another photon of any random frequency, when the electron is jumping down, if it collides with an electron or if it collides with a photon of any random frequency, then the frequency of the photon will be equal to the frequency with which it is colliding. That means, let's draw this again and show it to you. Nucleus, atom, the electron is jumping from higher energy level to lower energy level. The electron is jumping from higher energy level to lower energy level. Electron is coming back inside. Now, right? While it is coming inside, I'm going to make it collide with some photon. As a result, the light, instead of having its frequency, whatever frequency it was supposed to have, that is E2 minus E1 upon H, it will have frequency that will be equal to the frequency of the colliding photon. So now, if the electron is coming down and if I have one photon coming in, this photon is going to get, I will have two photons coming out from here of identical frequency. I would have two photons coming out here of identical frequency. One, the photon energy which I had supplied. Second, the photon energy due to the electron that is falling. But the beauty of this process is that instead of, see, when the electron was falling from higher energy level to lower energy level, it would have had some frequency of its own. But due to this collision, now it will have frequency which will be equal to the frequency of the colliding photon. Now, as an external person, I can control this particular frequency of the colliding photon. That means I can control the frequency of light that is going to be given out. Instead of one photon, I have two photons coming out. That means there is amplification, and I can also control the frequency. That's your basic principle of amplifying light. That is how you amplify light. Instead of one photon, I would have two photons coming out. That also of the frequency that I desire. Do you understand this? So do you understand this? What is stimulated emission? Right? In stimulated emission, I control the frequency of light that is going to be coming out. Right? How do I do it? By colliding the electron that is jumping from higher energy level to lower energy level with a photon of the desired frequency. Right? Let's just write this down quickly. Consider an atom in higher energy level. How did I bring it in higher energy level? By spontaneous absorption. Now suppose a photon of correct energy from some external source collides with the atom. From some external source collides with the atom. Right? The photon forces the electron to fall. This photon forces the electron to fall. This photon forces the electron to fall into the lower energy state. Into the lower energy state by emitting a photon. This is called as stimulated emission. Fine, do you understand this? Now the importance of stimulated emission is that the emitted photon has the same energy and the same frequency as that of the incident photon, and travels in the identical direction as that of the incident photon at the same time. The importance of stimulated emission. The importance of stimulated emission is that the emitted photon has same energy and frequency as that of the incident photon. And travels in the same direction as the incident photon. Fine. Now, viewed as a wave, you will see that there are two waves that would be emitted. So I would just see one wave going in. If I look at just the input and the output, what I would see is that only one wave is going in and two waves are emerging which are in phase and have the same frequency. Due to the constructive interference that occurs, this leads to a more intense wave. So stimulated emission leads to a more intense wave. Why? Because there would be, instead of where I had only one wave going in, I have two waves coming out, and both of them are in phase and have the same frequency. As a result, constructive interference would take place between them, and that would lead to the increase in the intensity. Right? Okay, we'll stop this here for the day. Thank you very much.